Let's have a colorful talk on finitary coloring by Alexander.
Okay, thank you very much. It's wonderful to be here. I'm actually going to be giving a second talk on a very closely related area to this one at the British Mathematical Colloquium. I hope I got it right, which is these dates. It's here in Cambridge, and I believe that's when my talk is, the 31st of March. And the titles are extremely similar, but the topics are disjoint and yet very closely related. So if you enjoy this talk, you probably enjoy that one as well. And if you're not around for this, then please feel free to come and ask me about the second topic. Well, that's right. That's the conference, and that's my talk. I think I'm not sure, I hope I got the dates right. Well, that denotes whatever the appropriate interval of times is. So you have to take the Cartesian product of that's right. I wasn't expecting so many questions on this first slide. Okay, so this is joint work with David Wilson and Oded Schramm. Not really necessary to say with this audience, but of course Oded Schramm, leading figure of his generation in probability theory, passed away in a tragic hiking accident 2008, so 6 and a bit years ago. So needless to say, he left many ongoing projects, and there have been many papers with Oded as an author appeared since then, and we've been a little slow finishing writing up this one, but this one is finally completed as well. So, of course, it was a real privilege to work with Oded on it. So, what's the question? So, let's think about colorings of a graph. So, a Q coloring, or proper Q coloring of a graph, is probably exactly what you think it is. It's a labeling of the vertices with the integers 1 up to Q, and you think of those as colors, such that adjacent vertices have to have different colors. Okay, so that's exactly what you think. So, okay, for instance, on Z2, well, there exists a 2 coloring. It's a bipartite graph, so we can color it with 2 colors, red and blue. Well, okay, here's a vague question. Can we color without any central authority? So if you imagine that each vertex is somehow a person or an independent agent, so can they agree on a coloring between themselves without any central dictator? And so, okay, let's try to be a bit more specific. So what about stationary random colorings of ZD, for example? So, well, again, in Z2, Z2, there are precisely 2 deterministic 2 colorings. You can do a checkerboard one way round or the other way round. Those are the only 2. And if you want a stationary random 2 coloring, then you'd better take this whole thing on the left with probability half and this whole thing on the right with probability half. That's all you can do. So that is a stationary 2 coloring, of course. But this isn't really what I want, because this has very long range correlations. So, you know, if I tell you the color of this vertex here, if I tell you it's blue, then you know you're in this coloring, so you know the coloring of everything else. You know coloring of vertices far away. So the sort of the Yeah, so it's more than correlation. It's something much stronger. So the sort of questions I want to ask is can you do better than that? So, okay, I mean, clearly you can't make the colors IID. If you have a finite number of colors and the vertex colors are IID, then there's no way you can get a proper coloring. But maybe you could get some sort of approximate independence, and there are many notions of approximate independence, of course. There are mixing conditions, there's tail triviality, there are decay of correlations, and so on. So this is the general area I want to work in. And so unlike, for instance, in Ron's talk earlier, I'm not really concerned about specific canonical models of random coloring. I'm more asking, can you do it type questions. Does there exist a coloring with good decay of correlations and so on? Okay, so here's the particular notion of approximate independence that I want to focus on, which may not be so familiar, but it is rather a natural notion in this context. So suppose you have a process X, random variables, a family of random variables indexed by ZD. We say it's a finitary factor of an IID process, which I'll abbreviate to FFIID, if, so three conditions, you have some IID random variables, UV, indexed by ZD, and the process you're interested in, X, is a deterministic function of that family of IID random variables. So all the randomness comes from some IID coin flips or dice rolls or something on the vertices. And number two, I want my process X, the one I'm interested in, to be stationary. In other words, translation invariant in distribution. So the way to ensure that, the natural way to ensure that, is that the function is translation equivariant, which means it commutes with translations. So you have your function which takes as input a bunch of IID random variables and spits out a coloring, and I want it to be the case that if you shifted all the IID random variables to the right by one, then you would end up with a coloring shifted to the right by one. So it's very natural. It just says the function doesn't treat the origin in a special way, it just does the same thing everywhere. So that, of course, guarantees that X will be stationary if 1 and 2 are true. And incidentally, if 1 and 2 are true, then it's said to be a factor of an IID process. And number 3, the most interesting one, I want it to be a finitary factor. And what does that mean? It means that think of it this way. Think of the function as an algorithm which looks at the IID random variables and then computes the process X that I want. It's going to be a coloring. And I want it to be sort of local in the sense that if I want to know what is the value of X at the origin or any other vertex, then the algorithm computes that value by first of all looking at the IID label at the origin, the U at the origin, and depending on what it sees, maybe it looks at the neighbors of the origin and looks at the IID variables there, and again depending on what it sees, maybe it looks one step further, and so on. But then at some point it knows and it decides what value to put at the origin depending on what it sees. So it has to look to some radius which may be random and depend on the IID labels that it sees, and maybe an unbounded random variable, but it's a finite random variable, an almost surely finite random variable. Okay, so that's the definition. So and well, okay, I mean, if you want it to be, if you want a formal definition, can people see this light color, by the way? I'm sorry, it's not coming out very well. It means that there exists some radius that depends on the U's, the whole process of U's, so that if you have two families of IID U's that agree on a box of radius r, and it's a box in the L infinity norm here, but it's not really going to matter, then the resulting values at the origin agree, and then I set capital R, very important quantity, to be R of the actual random variables. So capital R is called the coding radius, so it is this random distance that the origin has to look to determine x0. Okay, so it's a bit of a mouthful, but is the definition clear? If not, please do ask. Okay.
The lemma that R is appropriately measurable.
Yeah.
Yeah.
Well, I don't know if it's a lemma or part of the definition, but anyway, I want that to be the case. So it's kind of like a stopping time. It's kind of like a high-dimensional version of a stopping time, because in a stopping time you have time and you take one step after another until suddenly you know it's happened. So I'm doing the same thing. I'm looking at a ball, getting bigger and bigger, until at some point I know I can stop and I can decide what symbol to write at the origin. Okay, so this is what I want to look at. So the question I want to focus on is, does there exist an FFIID coloring, finitary factor of IID coloring? And if so, how small can we make this critical random variable, the coding radius, the distance you have to look to as a random variable? How does the answer depend on the number of colors and the dimension? Easy cases. You can't do it with two colors on ZD. We already saw that, because the only stationary two coloring of ZD is this thing where you're that checkerboard with probability half and this checkerboard with probability half, and it's very straightforward to see that is not an FFIID process. There's no way you can get that from coin flips in a translation invariant way. And also, obviously, you can never do it with the coding radius R being identically 0, because that means you don't look at all beyond the IID label at the origin, so that just means that your coloring itself is an IID process. But a proper coloring cannot be an IID process. Okay, so those are trivial cases. And this question has some applications in computer science. Imagine you have a network of machines, so some graph machines or computers connected to each other somehow, and maybe the colors, so I want to assign a color to each machine, and maybe the colors represent schedules for them to update their software, or maybe communication frequencies, and there are some local constraints, so you don't want neighboring machines to be in conflict with each other, so perhaps you don't want them to use the same update schedule, or you don't want them to use the same communication frequency, so that means you have to have a coloring. So the question is, can the machines choose colors for themselves in a local distributed manner, where the machines use their own sources of randomness, and then maybe they discuss with their neighbors and maybe their next door's neighbors, but then eventually they decide what color to be with a rule that's the same everywhere. And if that's possible, then you can ask, how locally can you do it? So how far does a machine typically have to look to? All right, so that's the question. So here is one thing you can do quite easily. On Z2, the square lattice, there exists an FFIID for coloring with exponential tails for the coding radius. The probability is greater than R, decays exponentially. And here's a pretty easy way to do that. So first of all, color the lattice with two colors, black and white, just independently. So flip a fair coin for each vertex and color it black or white. So then percolation theory tells you that because 1/2 is smaller than the critical probability for site percolation on Z2, the black and white clusters are finite. So here's a white cluster, or part of one, and here's part of a black cluster. And what's more, they're rather small. The diameter of the cluster containing the origin has exponential tail decay. So then what I'm going to do is simply checkerboard. So each white cluster I'm going to colour in two colours, red and blue, according to a checkerboard pattern. And so I do that for that white cluster, and for this one, and for this one, and then each black cluster I colour in two other colours, green and yellow. Again, according to a checkerboard pattern, this one, and this one, and this one. So the only thing I have to be careful with is how do I mean, why isn't it the same problem I had before? So on this white cluster here, how do I decide which of the two red-blue checkerboards to do? How do I decide on the phase? Well, I just have to do it locally. So one thing I could do, for example, is just start from the northeast corner of the cluster. Look at the lexicographically largest point in Z2 in the cluster and decide if it's a white cluster, that is going to be red. And then choose the checkerboard appropriately. So, okay, that's okay, that works, because, so why is that FFIID? Well, if I'm sitting at the origin, how do I discover my colour? Well, I have to explore my cluster, my black or white cluster. So I have to explore the cluster itself and its boundary to make sure I've found a cluster, and then I have to find the northeast point of that cluster and you know, call this guy on the telephone and say, you know, what colour are you? And then I can compute my colour. Right, so that's, and because the cluster has exponential tails, so does the coding radius. So pretty easy. Now, you might think this going to the northeast corner is a bit ugly, and in particular, one drawback is this process is only translation invariant, and that's all it had to be according to my definition, but you might see if you could make it rotationally invariant as well, or indeed isometry invariant. So, so there is a way to make it isometry equivariant, meaning that it's, you know, it's still a factor of IID random variables, but now the function commutes with all isometries of Z2. So one easy way to do that is, so in addition to these black and white labels that I start with, for every vertex of Z2, I choose an independent uniform 0, 1 random variable, independent of everything else. And then I look in my white cluster and I find the site with the largest uniform random variable, and I decide that that vertex is going to be red, and all the other sites in the cluster have to follow suit. Okay, so that's rotation invariant as well, and then, you know, it's a finitary factor of the IID process that consists of the black or white coin flip plus the uniform random variable for each vertex. Okay, so pretty straightforward stuff. So obvious questions are, can we do better? So already this R has exponential tails, so that's pretty good. It's a pretty small, well-behaved random variable, but can we do better? Maybe we could make R bounded. That would certainly be better. What about other D? So, you know, this wouldn't work in 3 dimensions, I think, because I think PC in 3 dimensions is bigger than a half. So, sorry, other way around, less than a half. And what about other number of colours? Can we do it with 3 colours?
But in 3 dimensions, we start with the coloring which is not black-white, some higher number, then it would work.
Right, that's right. Yes, good. So you can do it with some number of colours in any dimension. Yes, very good. So, you know, so what's the best you can do in terms of number of colours and dimension and tails? Right. So we know most of the answers to this. So let's look at ZD and 2 or more dimensions. So let's look at 3 colours. So can you do 3 colours? The answer is yes, you can. So there exists an FFIID 3 colouring with, but not as good decay. Power law tail decay on the coding radius. And actually you're not going to beat that, because any FFIID colouring, 3 colouring, has infinite second moment of R. Okay, so 3 colors, the answer is you can do a power law, but no better. Yeah, we have an explicit bound on this A, but unfortunately it's very, very far away from 2. So one of the open questions is, even in 2 dimensions, what's the best power you can do? Somewhere between 2 and something very, very small. That's all we can do. All right. What about 4 colors? So we already saw that you can do exponential tails. Can you do any better? Well, it turns out you can do better. You can do, there exists, with just 4 colors, any dimension greater than or equal to 2, you can do a tower function. So the probability you're greater than R is 1 over a tower of exponentials of height about R, or constant times R. And actually that's the correct answer. That's tight, because any colouring with 4 colours or any 10 colours, any larger number, satisfies a similar lower bound with a different constant, of course. So of course, it's arguable how tight these bounds are, because the constant makes a huge difference to a function like this. But that's the correct form. So 3 colours, it's a power law. 4 colours, it's this crazy tower function. So somehow it's very, very nearly a bounded random variable in some sense. The tails are very, very small, but they have to be there. So this was in 2 or more dimensions, and actually in 1 dimension it's slightly different. In dimension 1 you no longer have this special case for the 3 colouring, and for even with 3 colours you can achieve this tower function. That's in 1 dimension. Okay, so those are the answers. Let me show you how we prove some of these things. So first of all, let me do something quite easy. Here is a way to 3 colour the square lattice with power law tails. So think about a unit square of Z2. So you only have 3 colours and you have 4 vertices of the unit square. So you'd better have 2 diagonally opposite corners of the square have the same colour, because otherwise you're in trouble. So either this diagonal pair or this diagonal pair have to share a colour, perhaps both of them. So I'm sort of going to use that. So in each unit square, draw a diagonal, either this way or this way, with probability half each. Flip a coin for each square. And this pair are going to have the same colour as each other. Now, okay, look at this pink picture. What do you see? Well, if you look at the even sublattice of Z2, so you just look at the every other vertex and look at the diagonals that are incident to these vertices, then you know, for any 2 diagonally adjacent green vertices, either you have the diagonal joining them or you don't, with probability half. So the green picture is simply percolation, bond percolation on a rotated lattice with p equals a half. So that's good news, because we know lots about bond percolation with p equals a half. So it's critical percolation. So the clusters are finite, the green clusters are finite, but they have power law tails. They're quite large. On the other hand, what about the remaining pink diagonal lines? Well, those are precisely the dual percolation configuration on the dual square lattice. So we know everything about that too. So that's just another instance of critical bond percolation. And it has lots of nice properties. So every green cluster is surrounded by some pink cluster, and vice versa. Every pink cluster is surrounded by a green cluster. So put it another way, if any pink and green cluster, if they're adjacent to each other, then one of them surrounds the other. It contains a cycle that goes right around the outside of the other. So it's a very nice structure. So we will assign a color to each cluster, one of our three colors, and that will be enough that will give us a three coloring, provided adjacent clusters like this green one and this pink one receive different colors from each other. That's all we need to do. So this is the closest I get to a random graph or a random tree. So what does the adjacency graph of these bond percolation clusters and their duals look like? So, well, it's a tree. It's a one-ended tree. So so each node here represents one of the clusters in the previous picture, a green or a pink cluster. And I have to be careful because I have to sort of treat the green clusters and the pink clusters the same as each other, because I don't want to fall into the trap at the beginning of choosing one of the two checkerboards. I'm not allowed to do that. I have to do the same everywhere. So they are primal and dual, but they have to be treated the same. So here each node represents a green or a pink cluster, and two of them are connected by an edge if they're adjacent to each other. But if they're adjacent, then one of them surrounds the other. So I draw it so that the one above surrounds the one below. Okay, and it's a one-ended tree. It's a tree, and there's one way to go to infinity, which is up, and when you go down, you eventually end up at a leaf. Okay, so all I have to do is assign a color to each vertex in such a way that it's a coloring of this graph, and then I have to make sure I don't ruin the power law property. Okay, so this is pretty straightforward. First of all, why don't I try just color each node of this tree red with probability half independently? Well, of course, that's not going to work because I may have adjacent red things. But now if I colored a vertex red, but its parent was also red, then I'm going to take it back. So if I colored something red and its parent was also red, then I uncolor it, delete the redness. So this gives you a collection of red vertices, no two of which are adjacent, and it sort of has some good properties because if you're working on the tree, then and I start at any vertex and I go upwards until I meet the first red vertex, I'm not going to have to go very far. It has exponential tails pretty clearly. I just wait until I find something where the coin came up heads and the parent came up tails. Okay, so that seems good news. That seems like that won't hurt this power law bound that I'm trying to get. So I delete those guys, and now I just have to fill in everything else. So for example, I can do it in layers. So below a red vertex, the next layer I make everything blue, and the next layer I make everything green, and so on, and until I get to another red vertex, and then from that red vertex I start again. So below this one everything is blue, below that everything is green. Okay, so it's a straightforward way to do this. And then, yeah, so this works, and so to actually prove that it's FFIAD with a power law, you have to think a little bit, but Russo-Seymour-Welsh estimates will do it for you. I mean, you think you're at the origin, you're in some cluster, think about the sequence of surrounding clusters of that one, and just look how far you have to go up the tree until you get to one of these red guys, and then at that point you know what to do. That's the idea. But because it comes from Russo-Seymour-Welsh, our estimate on this A is terrible. It's very, very close to 0. So interesting question whether that can be improved. So we also managed to do it on ZD with only 3 colors, and this is considerably harder, but it's the same kind of idea. So first of all, we define a hierarchical construction of a partition of ZD with a tree structure, a one-ended tree structure, kind of similar to the clusters. So you have a partition of ZD into sets, and each one has a parent, another set that surrounds it. All the sets are finite, and there's a way of constructing this thing with power law tails from IID randomness. It's a pretty intricate construction. I don't know whether there's a simpler one, but it involves putting down random seeds of various intensities and taking balls around them and carefully intersecting balls and so on. So you can construct this thing. Now these sets are not quite like the green and pink clusters in the previous picture, because remember the green and pink clusters were along the diagonals of Z2, so each cluster was itself an independent set in the graph, so I could assign it a single color, and now they're not, they're actual regions of space. So what I have to do instead is assign a proper coloring to each of these cells, and I'm going to assign one of the possible checkerboard colorings using 2 out of the 3 colors. Okay, so I have 3 colors to play with. There are 6 ways I can color with a checkerboard, because there are 3 pairs of colors and I have to decide which way round they are. And I'm going to assign one of these to each of those cells, but there are some rules about what I can put adjacent to what. So if I have this red-blue checkerboard coloring, then I could put the red-green one next to it, because the red is in the same corresponding place. So if I put those next to each other, the reds don't clash with each other, and I've just replaced blue with green. Right? And so on. So if you figure out the allowed adjacencies, it turns out it's a hexagon. But it doesn't really matter. All that matters is the graph is connected. So the idea is now we do the same thing, but we're going to assign these checkerboard colorings. So again, there's this tree structure of the family tree structure of these cells of my partition, and again I define some special cells in a similar way to before. Now they're further apart, they're not just an independent set, but some set of special cells that don't come too close to each other. And the idea is that each special cell chooses for itself a checkerboard coloring. So this one, in its dreams, it really loves this green-red checkerboard coloring that it chose at random, independently of everything else, and it really wants all its descendants to use that because it's convinced it's the best coloring in the world. But unfortunately it comes with some baggage, because it has some ancestors as well, and somewhere up there's some other guy who's trying to force this guy to use something else. So maybe he himself is actually forced to use this guy, but he doesn't mind. He knows he can transform this to this in a suitable number of steps. So you work down from that special guy, and well, in the first step you can go to this, but then in the second step you can go to this dream coloring that he really loves. So everyone below him he forces to use this, and until we get to another special guy, and then this special guy gets to take over this process for the guys below him. So that's the idea. And yeah, again, if you do this carefully, you get a power law bound, and the power is even more terrible than it was in 2 dimensions. So we don't know what the right power is. So why can you not do better than a power law with 3 colors? I won't show you the whole proof, but I'll show you key ideas. Right, so in fact we claim any 3 coloring you have to have infinite second moment of the coding radius. And it's enough to prove this in 2 dimensions, actually, because if I have a FFIID 3 coloring in 3 dimensions, then just restricting it to the plane, I get an FFIID coloring in 2 dimensions, and I have to be a little bit careful because it depends on the IID labels in the whole of Z3, but I can think of the ones in a column as a single random variable. So it really does work. It's enough to prove it on Z2. And so in fact, there's something stronger is true. Any stationary 3 coloring has fairly slowly decaying correlations in a way that implies this. And the key idea is there is a height function for 3 colorings on Z2. People are nodding because many people know this already, I'm sure. So if you have a 3 coloring of Z2, you think of the colors as 0, 1, or 2, and along any edge, of course, the colors are different, and that means if you think of them as numbers mod 3, they differ by one way or the other. So if I'm going from 0 to 1, that's going up by 1, and if I'm going from 0 to 2, that's going down by 1. So the height function is the thing that's supported on the whole of Z that goes up or down by 1 in the corresponding way. And it turns out, that really works. If you try to do that, you have to start somewhere and decide, okay, this guy is going to be height 3, and then you can reconstruct all the rest, and it works. You never get any contradictions, and to check that, you just have to check that it works around a unit square. Okay, so there's this nice height function. It's a 1 Lipschitz function, and the point is that since it's a height function, if you take a big contour, a big square, then the total height change as you go around the square must be 0. But on the other hand, you can see what the height change is locally, because it just depends on these differences. So if you take a big tour around the square, if the correlations decay fast enough, then it seems very unlikely that it would come back to 0, and that would mean you can't fill it in a coloring. So that's the idea. So height change around a contour must be 0. Turns out even if the process is tail trivial, which is implied by FFIAD with suitable coding radius, then the variance of the change along a side is large, and here's the lemma that implies that. I'd be kind of curious if anyone's seen this lemma before. I'm sure it can't really be new, but we didn't actually find it, and we found a proof. I'm sure there are other proofs. If you have I hope I didn't miss any conditions out here. If you have a process on Z of plus or minus 1 valued random variables, stationary process, and right tail trivial, so that the right tail of the sigma algebra contains only events of probability 0 or 1, then either it's deterministic, which would mean it has to be all plus 1 or all minus 1, or the lim sup of the variance of the partial sums is infinity, almost surely. It's not so hard to prove, but it's not completely trivial. I'd be interested to see other proofs or places where this is published. Anyway, so that's what you use to get this. The variance of the change along a side is large, but on the other hand, if you have fast enough decay of correlations, then the changes along different sides are approximately independent of each other, because there's a side here and there's a side here, and most of this side is a long way away from most of this side. So you end up with a contradiction. When you go around a contour, there's no way that you can typically end up back at 0. Okay, so that's kind of how that works. Okay, what about this other side of the picture? So I claimed that with 4 colors you could do spectacularly well. You can get these colorings with tower function coding radius, and here is the basic idea behind this. So a lot of these ideas have been studied before in the computer science literature and motivated by applications in computer science, and what I'm about to tell you now is essentially something that was found by Cole and Bishkin in 1986. And I don't know, it's difficult to translate the results in some of these papers directly to the form we want, because somehow the focus is very different for these computer scientists, but essentially it's the same argument. So, okay, right, so how do I do this tower colouring? So let's just work on Z. So I'll show you how to do a tower colouring on Z with some number of colours. Not 4 yet, just some number. So I mean an FFIAD colouring with tower function decay of the coding radius. So the key thing is, suppose you have a labelling of Z with 2 to the n labels. I don't want to call them colours yet because it's not necessarily proper colouring, it's just integer labels, 2 to the n of them. Here's a way to reduce that 2 to the n down to essentially n, or 2n plus 1. So here is a labelling of Z with numbers between 0 and 7. Write them in binary and then do the following thing. Look at a consecutive pair of them, and if they are different, then write down which way round the inequality goes. So here 2 is bigger than 1, so write greater. And if they're different, write down the first digit where they differ, the first bit where they differ. If they're different, then one of their bits has to be different, and here the first one from the top is the second bit. Here it's the top one, here it's the second one. Here they're the same, 5 and 5, so I just have another symbol that I write down if they're the same. Okay, so what did I do? I ended up with a labeling, a process, a sequence using 2n plus 1 possible labels, because this could be greater or less, and there are n bits, and I have this extra star symbol. And the point is, I'm trying to produce a proper colouring. So I want adjacent labels to be different. Now, the only way I can get 2 adjacent labels different on the bottom level is if 2 labels were, the only way I can get 2 the same on the bottom level is if 2 were the same on the top level, just above it. Because, suppose 3 guys in a row are different like this, then these 2 are different and these 2 are different. So it's not possible, it wouldn't be possible for me to have greater than 2 and greater than 2 again, because that would mean that these 2 differ in the second digit and the 1 is to the left of the 0, and these 2 differ in the second digit and the 1 is to the left of the 0 in that second digit. So that's impossible. Right? So the point is, I by a very local rule that just involves looking at my 2 neighbours above me, I reduced from about 2 to the n colours to n colours, and I didn't really create any new colour clashes, any pairs of adjacent things that are equal. So in particular, if you do this, if you start with an IID sequence of numbers here from some huge alphabet, and you do this reduction k times, then each time you take the log of the number of symbols, essentially, and so do it until you have something like 6 colours, because at the end, if n gets really small, then this isn't a reduction anymore. At some point, 2 to the n isn't bigger than 2 to the n plus 1. So with something like 6 colours, you have to stop. But it means you get a process that's it's FFIID with coding radius something like k over 2 if you like, because that's the radius in 2 directions, with a fixed number of colours, and with it's not a colouring, but it's very, very nearly a colouring. The probability of 2 adjacent colours being the same is very, very small, 1 over tower of k, tower of exponentials of height k. Okay, so that's almost enough. So what I have to do is, if I want to get an FFIID colouring on Z, I stitch together these almost colourings somehow. I won't give you the full details of how to do it, but the idea is you have this sequence of 6 colourings, and I try to use the first one but the first one might have a few color clashes in it, but when I see a color clash, I use the better one that looks a little bit further and has a much smaller probability of a color clash, and so on. So you have to take a bit of care to do this to make sure you don't, in the stitching together, you don't produce new color clashes, but one can do this, it's not too difficult. So you can color Z with 6 colors, it turns out, and that immediately means you can color ZD with 6 to the D colors, because I can just take one of these colorings in each dimension and sort of intersect them. So that's good. So I can do ZD with some number of colors with this extraordinary tower function decay. Now, okay, but I claimed I could do it with 4 colors. So you can rather easily reduce the total number of colors to the degree of the graph plus 1. So in ZD, 2D plus 1, by just locally eliminating colors. So for instance, on the line, here's my 6 coloring. Whenever I see color 6, I'm going to replace it with the smallest number that I could write there. Well, what does that mean? It means the smallest number that's not the same as either of the 2 neighbors. And since there are only 2 neighbors, the biggest that could be is 3. Right, and then I do the same thing with the 5s, so I eliminate them, and then I do the same thing with the 4s. So then I'll end up with a 3 coloring, and I increased the coding radius a bit by doing this, but not very much. It still has tower function decay because it's just a local rule. I only have to look within a bounded distance. Okay, so that's quite straightforward. So the reduction to 4 colorings is considerably harder, but we were able to do it by starting from these colorings with some number of colors and also some long range colorings as well. So not on ZD, but on a spread out lattice of ZD, you can also get a proper coloring of that. And doing some, carefully chosen local reductions, similar to the ones I showed you, we were able to get an FFIOD process with tower function decay with two labels, black and white, and not a proper coloring, of course, but with bounded clusters. And then once you have bounded clusters, you can go back to the old trick. So it all comes down to the fact that in ZD it's possible to have, well, at least in Z2, it's possible to have 2 pairs of things meeting at a corner and neither of them are adjacent to each other. It's sort of what it all comes down to. So you have these bounded clusters, and then you can checkerboard each one, and because they're bounded, they really, each cluster only has at most size 10 or something. So this is just a local factor. It's a finitary factor with bounded radius going from there to there. So it's still has tower function decay. Okay. So finally, the 4th claim of the theorem. What about the lower bound? So why can you not do better than a tower function? So this essentially comes down to Ramsey theory. And again, someone else got there before us, Moni Noor, again motivated by applications in distributed computing, proved an essentially equivalent result to this, although again, if you read that paper, it's not totally obvious it's the same result, but it is. But arguably, it's really a manifestation of Ramsey's theorem. So anyway, here's the key thing. So I want to rule out the possibility. So again, it's enough to do it on Z. So I want to rule out the possibility that there's an extraordinarily good FFIID coloring with even less than this tower function decay. So suppose I have one. So then look at you see, for every vertex I have this random distance that I had to look up to to determine my color. So just look at the places where that distance is less than r for some fixed r. Okay, so the key lemma that you need is this, and this is just completely clean statement. Again, it kind of ought to be better known than it is, I think. Suppose you have a bunch of IID random variables. I don't care what space they're in, what distribution they have, and suppose I have a function of r arguments. This is supposed to be a blackboard build r, the real numbers, of r arguments that takes just discrete values, takes values 1 up to q, integers 1 up to q. And let's look at f of u1 up to ur, and then slide along by 1, f of u2 up to ur plus 1, and ask whether those two are equal. So the claim is that they may be equal. With some positive probability, they may be equal, no matter what function you choose. That's not obvious. So this is positive, and furthermore, there's an actual bound, an explicit lower bound on it, which is essentially a tower of height r and with a q somewhere at the top. And this is essentially tight by this other binary construction that I showed you before, up to like this constant 4 and so on. Okay, so let me just show you a proof of this, because there's a very simple proof, arguably simpler than this proof in the literature. Actually, I'll just prove that it's strictly positive. Okay, so for any function, any IIDUs, the probability they're equal is strictly positive. So it's by induction on r, the length of the block. When r equals 1, it's easy, because you just have IID random variables. So f of u1 and f of u2 are IID, and they're discrete valued. So of course there's some chance that they're equal. So now it's by induction on r. So for r greater than or equal to 2, here's the key step. Define a set-valued function of r minus 1 arguments. And what it is, it's the set of values that f could take when you fix the first r minus 1 arguments, but you allow the last one to be random still. So it's the set of colors, integers 1 up to q, so that if you fix the first r minus 1 and you still let the last argument be random, the set of a such that this takes the value of a with positive probability. Okay, so that is a set-valued function, so it takes at most 2 to the q values, because it's a set of the numbers 1 up to q. And it's a function of r minus 1 things. So I apply the induction hypothesis to that set-valued function. So it says that with positive probability, s of u1 up to u r minus 1 equals s of u2 up to ur. Okay, so far so good. That's the inductive hypothesis. So now, in particular, that means with positive probability, you can find, of course, a specific set A, deterministic set A, such that with positive probability they're both equal to that. Nothing fancy there. And now I can take a specific deterministic element little a of that set. And what about f of u1 up to ur? Well, on this event up here, this f lies in that set. I mean, almost surely even, because this is the set of values that can take with positive probability. So certainly it is one of them. So with positive probability, it's equal to the specific element that I chose. But now, okay, well, I haven't looked at ur plus 1 yet. So on the event that I have, let's look at ur plus 1. I haven't looked at that yet, so it's independent of everything else. So by definition, since this is one of the elements in that set, this might be equal to it with positive probability. So that's it. So with positive probability, those two are equal. Okay, so it's a little strange, but it's very straightforward, really. And now you can see if you do this a bit more carefully, where you would get that tower function bound from, because in the induction I went from q values to 2 to the q values, and I reduced r by 1. So you just have to do it a bit more carefully. Instead of saying with positive probability here, you have to say with probability at least epsilon, and choose the epsilon carefully, and then you get the tower function bound. Good, okay. So in the last few minutes, let me tell you a couple of extensions and open questions and so on. So colouring is just one of a family of questions that you could ask about local constraints. Colouring is a local constraint. It says that neighbours have to have different colours, but I could imagine more complicated local constraints. So the appropriate definition is a shift of finite type from ergodic theory. So this says so I'm on ZD still, and I'm going to define a set of allowed configurations. So I still have Q colours that are allowed. There's a set of configurations, and it's determined by insisting that every 10 by 10 box, say, I have a list of allowed patterns that I'm allowed to see on a 10 by 10 box. Just make some list of 10 by 10 boxes, and I say every 10 by 10 box has to be one of those allowed set. Okay, so that's the definition. So of course colouring is an example of that. It's just maybe I didn't write it right, but yeah, it is an example of that. It just says whenever you have two adjacent vertices, they have to have different colours. Okay, so you can ask what happens for a general shift of finite type, and in one dimension we know the answer. In one dimension, actually, there's nothing else. Colouring is canonical. So remember, in the main theorem, in one dimension we didn't have this power law case, we just had the tower function, and that's what happens in general. So if you give me a shift of finite type, you give me one of these systems of local constraints, then there are three possibilities, and 1 and 3 are silly, trivial possibilities. One is that there's just no FFIAD process that lies in S that satisfies your constraints, for a stupid reason similar to what happens with 2 colouring. Because with 2 colouring on Z, for example, you have this built-in periodicity. If you fix a red at the origin, then you know that there are reds every even spot. So there's some equivalent condition to that. So that's not an interesting case. And the other uninteresting case is, suppose you give me a system of local constraints which allows me to put some constant configuration, all ones, say, then I have no problem. Then there's an IID process. It's a deterministic IID process that satisfies it. So R is 0. So those are silly cases. So apart from that, for any such S, there exists an FFIAD process with tower function tail, and any FFIAD process has a tower function lower bound. So that's in one dimension. Big open question, what happens in higher dimensions? So take a shift of finite type, in other words a system of local constraints in 2 or more dimensions, ZD. We know examples of these 4 types. The 2 trivial cases where there's no FFIAD process at all, and the case where there's a constant solution. And we know we know cases where power law is the best, we know cases where tower function is the best, and there are 3 gaps in between here. So question, are there any other things in any of those 3 gaps? Any other local constraints that you can give me? So is there a local constraint that you can give me so that the best thing has exponential tails, for example? I mean, that's more, the regime we're used to working is sort of strictly in here, exponential tails, for example. I don't know the answer. And finally, beyond finitary factors, so this is a quick advert for my second talk that I'll give in a couple of weeks. So this is a different direction, also very interesting. A block factor is an FFIAD process with bounded coding radius. So that just means it's much, much simpler than the definition I gave before. It means you get all your randomness from some IID, random variables, and to determine my color, I just look within distance 10 and I can compute it, or within distance k. And, well, you can call it a k. In one dimension, you can call it a k block factor if it's a block of length k rather than 2k. Doesn't really matter. So, of course, the theorem says that there's no block factor coloring, because for an FFID coloring, you have to have this tower function decay, so it's not bounded. On the other hand, here's a slight variant, seemingly a slight variant of that condition. Call a process k-dependent if things that are distance k apart are independent of each other. So on Z, you can just say, provided it's a stationary process, everything up to everything on the negative integers is independent of everything from k onwards. Okay, so if you have a block factor, then it's certainly k dependent, and if it's a k block factor, then it's k minus 1 dependent. So an obvious question is, what about the implication in the other direction? And this question has sort of been around for a long time. It seems to have first come up, been raised by Ibragimov and Linnik. So this is a book in Russian, and they actually just asserted without proof that it's not an if and only if, but they didn't give any example. And then this was sort of stated as an open problem for several decades after that. The first counterexample was in 1989. So there is a counterexample. There exist stationary k minus 1 dependent processes that don't arise as block factors. It's not obvious at all. And the example they gave was interesting, but sort of very contrived and sort of an indirect construction. And they asked for a natural example, and there've been there's a lot of history of people trying to come up with a more natural counterexample, and really. All the examples that people have come up with are somewhat contrived, and they seem like they're designed specifically as counterexamples. Now, it turns out that coloring leads to a very nice and interesting answer. So there's a miraculous stochastic process that answers this question in a very surprising way. It's well, an astonishing process. So that's what I'll tell you about at the other talk, or you can ask me about it, of course. And yeah, that's it.
Thank you. So I counted, maybe I missed some colors, but I counted 14 colors, right? I'm not sure. Maybe. Are there any questions?
But 4 is enough.
Four
colors.
Good 14.
So you went from colorings to shifts of finite type.
Yes.
There are some intermediate things like graph homomorphism.
Right.
Do you know more about that?
No, I don't. Right. I mean, and I guess there are some. I didn't talk about it carefully, but there are some reductions that you can do. I guess. I mean, if you consider longer blocks and increase the number of colors, then. But yeah. But the answer is I don't know. Yes.
And something to do with your 3 coloring and lines. There is a reference of Pinson that is not maybe so far, but not exactly this.
I don't know much actually. Very glad to hear.
People who build wireless sensor networks
Yeah.
might want to deal with random geometric graphs.
Right. Uh-huh. Well, not specifically. I mean, what you can do is, and this is also appears in the computer science literature, but in different language, is you can, on an arbitrary graph, but of bounded degree, you can produce an FFIID coloring with degree plus 1 colors and with tower function tails, and in even stronger than FFIAD, you can make it so that if I'm trying to figure out my color, I don't even need to know the graph structure. I only explore the graph structure up to distance r and the random variables. So that can be done, and it's not too difficult. But yeah, the question of what happens when you, well, what happens if it's not bounded degree, but even more when you try to reduce the number of colors beyond that, I don't know. Would be interesting to try, maybe.
There is a work of coloring a Voronoi diagram in 2 dimensions.
Yes. That, well,
That's
right.
Omer and others.
Yeah, I mean that's is that finitary though, or is it just stationary?
I think it's both. It's deterministic. It's on the it's on the Poisson process.
Right, but it doesn't mean it's
I think
necessarily
it's
finitary.
finitary. I think so. But I forget.
So yeah, so I guess you can ask what the tails are.
Try to optimize the tails.
Right. Yeah. Yeah. So the focus here is very much on the tail.
No question? If not, let's thanks both speakers of the afternoon.